My name is Neil Barazida. I'm a data scientist here at DagsHub, which is one liner is the GitHub for machine learning. A bit about myself. So my background is my bachelor's is from the Ben Gurion University, where I studied structure analysis using finite element methods. And from structure analysis, I moved to data analysis, which was more natural for me. And then I did the IDC bootcamp, and I started working for Wolti, which is an Israeli-based startup company in the mortgage ecosystem. Not sure if you had it as an option back in your course. So I basically built machine learning algorithms to try to hack the way that banks calculate the mortgage rate for our customers. And like, I didn't really hack the bank, I just hacked the way that they calculate it. And we managed to reduce approximately 1% of the mortgage rate to our customers, which is a lot. And about a year and a half ago, I joined DagsHub, and like this rocket ship is about to leave Earth straight to the moon. And here we're building, basically, we're in the MLOps ecosystem, and we're building the GitHub interface for machine learning. We're basing everything on Git, but basically we're integrated with a lot of open source tools that provide an holistic solution for data scientists to build projects and collaborate together. And I think with that being said, any questions before I share screen and start talking? Anything you want to talk about before?
It's like GitHub for data science, like you said, and
exactly.
Like, instead of code and stuff like that, it's notebooks.
No, so you're getting the GitHub UIs. We're gonna see it in just a bit, but basically you're getting all the GitHub core features. So file view, like a Git server that you can track and version your files with Git and push it to there and see it on DagsHub, but also experiment tracking table, storage that is connected to your repo, data version control, pipeline, annotation. So I think it's relevant for the people who are doing the computer vision projects, but also audio, whatever. So if you need to annotate your image and create labels, then you can easily do it with DagsHub. So we integrated Label Studio to the platform. But maybe I'm diving too deep, too fast into DagsHub. We're going to see everything in just a bit and see like how everything connects there. Cool. So I'm going to get started by sharing screen, which is probably the hardest part in the Zoom sessions. Okay. And let me know if you can see it.
We're seeing something.
Yes, we got
teamwork that scales.
Exactly. So this is the workshop that we're gonna have today, and we're gonna talk about how we can collaborate together on data science project in a way that is scalable and not being lone wolves, which is basically a lot of the use cases that we currently see. So what are we going to cover today? So we'll start by exploring why collaboration and teamwork is essential in any project, and especially in data science project. We'll then talk about what are the barriers for collaboration in a data science project, and what are the root cause and how it affects our work and productivity. Then we're going to discuss about the element of solutions. So what will help us overcome those challenges. And then, and this is going to be, I know it only took one bullet point, but this is going to be the major chunk of this session. We're going to learn about open source MLOps tools that will help us overcome those challenges. So the ratio here is like 1/4 to 3/4 in bullet points, but in the time it's going to be the other way. So most of the time we're going to talk about those tools and how to use them and how we can leverage them. So a very nice saying that I love to use is teamwork makes the dream work. And this is a phrase that you probably heard, but sometimes it's elusive. If you ever worked in a team that really clicks, you'll know how true this sentence is. And you know how productive you can be when you're working in an efficient team. However, when we see or when we approach collaboration in a data science project, we most of the time see lone wolves than harmonic teams. So this is because collaboration is actually not beneficial for us. So no, I beg that saying. I think that collaboration on data science project has many advantages, both for the company and for the practitioners, and we should work in teams, but in a way that enables us to scale our work, and the same as we are able to scale our work on software development project. So the ability to work simultaneously and develop features side by side without stepping on each other's toes. And what will benefit out of it? So it will enable us to move faster and scale our work by either putting more men or women power on a specific task or divide the task or the problem between different team members. We'll not have a single point of failure. And in a system, it's like a critical risk that we don't want to have. We should avoid bottlenecks, personnels, and have redundancy inside the team. We also want to have a higher variance of capabilities inside our team that will allow us to adjust the capabilities of the team members to the task at hand. We also want to be able to share the knowledge between team members, and this is a known fact that it accelerates projects. And also, if you disagree with everything that I just said, and you say, no, I don't need to collaborate with anyone, so you're probably gonna collaborate with someone, and this someone is the future you. So think about maintaining a production model that you deploy, let's say, a week ago, a month ago, 6 months ago, whatever. It's going to be very hard for you to understand what is the root cause, which exact model did you deploy, what data did you use to train it on, which code generated it, and all of those things are going to be very hard for you to do. And this is a different kind of collaboration, but we all face it when we're working in a production-oriented environment. So why aren't we seeing more collaborative work in the data science ecosystem? Well, based on we're doing our MLOps research inside the company, where we conducted interviews with more than 100 companies worldwide with many data scientists, machine learning engineers, and team leads. And we found several common challenges that has two root causes. And the first and foremost, the first challenge that we see, or the root cause, is that unlike software development projects that are mostly composed out of code, a data science project is composed of a variety of artifacts such as code, data, models, pipeline, experiments, and I can go on and on and on. And each component has unique characteristics and requirements. So for example, code files are lightweight and can be hosted on our Git server and can be easily diffed by text editors. But our data and models are much larger and can be versioned easily with Git or stored on Git server. So we're going to use a different tracking tool and use a different storage for them. Same for experiments, pipeline, and more. We also need a way to sync between all of those components. So the train model, as we said, that we just deployed to production, we use some code to generate it and some data set. And once we deploy to production, we need a way to connect that model to the relevant code and data. And also we want explainability, understand how the components work together and form a pipeline. And currently it's a bit harder to do. There are a lot of companies that are attacking this problem, but it's very hard to understand what is going on in the project. And how does it really affect us? So first of all, onboarding a new project that already has a code base, models, and more can be very time consuming and very hard to do. Unlike code files or code that you only need to go over the relevant code files that you in charge on or gonna take on, data science project, you need to understand the different data and like the different types of files that you have, all the different components, but also understand the research that was already done so you won't repeat previous research steps. And this is also something that can be time consuming. We want to work simultaneously on different components of the project, which is it's not well defined currently, has a lot of blind spots and needs to be carefully managed and synchronized. And debugging, we said it a lot, it's very hard to do. And not only the variety of artifacts causes all of those challenges. Also, being in a field that is research driven and the need to explore many solutions to a problem, it's the core principle of data science. And there is no clear golden path that leads us to the top of the mountain. Some trails can be shorter, some longer, but what is certain is that there is more than one way to achieve the final result when we talk about data science project. And this fact is, or this is like basically a huge challenge for us, for our workflow, which is not sequential, but more of a like skip connections flow. So we don't really know what is going to lead us to the best result. It can be the first try, the 10th experiment, or the 100th experiment. And therefore, we can't simply merge the tip of our branch to the master branch. We're going to probably need to reproduce previous results, go back in time, and then merge them to production. We also need a way to log the different experiments and the different hypotheses that we try to search for in a way that will also connect the experiments, the code, the data to the relevant log. And how does it really affect us? So reproducing results become an excruciating and not well-defined. We need to reproduce all the relevant artifacts that are tied to that experiment. And currently, it's not trivial to do. When we want to review other people's work, it either can be very time-consuming, and if we don't want to consume all of our time, we're going to do it superficially, and eventually it's going to, once again, cause bugs in production, which we don't want to have. And we're also going to lack the research history of the project. So as I just said, we don't want to repeat previous experiment that already we conducted. So let's say I'm leaving the team and Asi is joining, and we don't want Asi to repeat my previous work, right? It's going to be time consuming. So this is why we want to log our knowledge, to have our knowledge management. And
question?
Yes.
Going back to what you said, is just so you're having success with all this part of can you go back one slide with all this part of reproducibility and all that stuff?
So currently it's hard because think about it, you're running different. You're running different. You feel it, right? It's
and I have, for example, now I'm using I have in my own work a model that I made a year ago, and it's very good, but I have no idea yet what I did to achieve it because I lost what happened.
Classical. So, please write a testimonial for us.
If you can do something like this, it's amazing, I think.
So just wait a few more slides and you're going to see the magic happens.
Okay.
So yeah, so reproducing results is like a huge pain. We found an easy way to do, I would say an easy way to do it, which is very efficient, that allows you to just like revert back with a single git command. But stay tuned, as they say. Cool. So after doing the extensive research, as I said, we understand that in order to improve our workflow and overcome those challenges, we need to have 6 core capabilities that are data science oriented. So the first thing will be treating all the project artifacts as a first-class citizens. So not only our code files should be versioned, diff, and visualized, we also need the ability to visualize and diff notebooks, models, data files, pipelines, and basically everything that composes our project. We want to also easily and efficiently track our different experiments and the ability to easily compare between the different experiments, so we'll know which one provided the best results. Next, we want to version control all the project components. So we now created that experiment, but we don't have the relevant version of our data or our model or probably our code we're going to have it, but we want a way to also version all of those components. Next, we'd like a way to reproduce all of the previous results that are relevant for us. So not all of the different experiments, but just the best ones that we were able to achieve. And by doing that, we want to have a way to easily review the process or the research that was made and easily see what changes were made to all project components and compare them to what we currently have in production. So we have our experiments that we ran, we version control all of our project, we're able to go back in time to the best one, we were opening a pull request, and now what? If I can only view our code files, that will be actually meaningless. I want the ability to compare between the best experiment in the pull request to what I currently have in production. I want to go over the code to see that you didn't have data leakage. I want to see the data that you used. So basically, I want to review all the different project components. And last, we want to use CI/CD tools to easily deploy our models to production, test the relevant files, so test our data files, test our models. So the same as we're testing our code files before deploying to production. A side note, DeepChecks is an open source tool for that. Highly recommend it. Check it out. I'm not going to cover it on this session. So based on those elements, yes?
You can use it, all these things you explained on GitHub, or just special for DagsHub?
So I'm now getting to it. So basically GitHub that provide very good solutions, but for software development. And basically what we're doing here is taking that idea or that approach and implementing it for data science and machine learning. So we're just going to see it in a bit, how we're doing it. That's actually the next slide. So it's in that sense, it's a good question because I have slides for it. So based on those elements that we just covered, we built DagsHub. And in a one line, DagsHub is the GitHub for machine learning, a place where data scientists can host all of their project components in one place. And to start on how are we actually doing it, I'd like to start with what we're not doing. So we don't try to reinvent the wheel wherever it's not necessary. We simply rely on existing solutions for the challenges that we're trying to solve. So we see and we know that there are a lot of powerful open source tools out there that provide part of the solution, but there is no one golden magical tool that can be great at everything, right? So it's probably going to be mediocre in everything. So what we believe is by simply integrating all of those tools that best suits your needs under one rooftop and add a workflow layer above them will provide an holistic solution for our users. And how are we actually doing the research here and the integration? So when we approach a new problem after doing a heavily research about what is the current the most pain that data scientists face currently, we then do a market research for you. We choose the best suited open source tools out there that are that provide a solution for the specific task in hand, and we prioritize it by the ease of use. How flexible are those tools? If those tools support as many workflows as possible, and we also see if they have active community. So and how well maintained are they? Once we find the best tool that fits that challenge, we integrate it into the platform in a modular way that won't force you into using it, but you'll be able to choose if you want to use that tool or not use it if it's not relevant for you. So let's say you just want to version your data and you don't have any use for data annotations. So you don't need to use the annotation capability. You can use the tools that are relevant for your specific problem. And on top of that, we are doing the DevOps heavy lifting for you and adding new capabilities to those tools. So that is the top layer, the layer that we're adding above all of those tools. And in most cases, all you're going to need to do is copy a few lines of commands to your terminal, and you're set to go. And by doing that, we're putting those tools under one roof and adding the Git workflow there on top of them. We're turning this workflow that looks very disorganized into this workflow. And here you see that you have a single source of truth to all of your project components, and it's under the same place. So you don't need to move around from different platforms. So you have your code files on GitHub, and your data files on an S3 bucket or storage or Google Drive, and your experiments on a MLflow server, and I don't know what else, and your labels on an annotation platform. So you're gonna get all of those capabilities or those tools under DagsHub with an additional layer that provides that workflow that you can use. And what will you gain, or what our users gain when they use DagsHub? So this is what we, the insights or the feedback that we get from our users, that first of all, it helps them to onboard faster of new team members to existing projects. They also have a structural way to hand off project between teams. So now the data science team finished the research phase and now they want to ship it to production. So the MLOps team can simply take it and deploy the models, and they have like the specific Git commit that they need to deploy, and also using CI/CD tools. You can also split work between team members and work faster and reduce the iteration time from research to production. And last, reviewing each other's work is much more efficient, easy, and bug-prone. So it's the data science pull request is a core feature that we focus on, that you can actually review all the different components in the project and make sure that you're not deploying bugs to production, which is also very important. So I think at this point, it's a good time for a short demo. Do you have any questions so far? Awesome. So let me share the relevant screen. Let me know when you can see my screen.
We can see it.
Awesome. So this is DagsHub. We explored it just a bit last time, and I want to dive into the details and also show you how you can use your GitHub project with all the DagsHub capabilities. So stay on GitHub and also use DagsHub for it. So I'm going to start by going to SaftaDepth, which is an open source data science project that we're maintaining, where we're trying to take 2D images and predict the depth dimension. And this, you can easily see that the UI here is very similar to the GitHub UI, right? I think Asi asked about it. Or no, I don't have your names here. So one of you just asked about it. So this is basically what I mean by providing the GitHub interface and the GitHub capabilities. So you have the file view, you have the issues, the pull request, all the core capabilities that you have on GitHub, but you're also getting the experiment tab, the annotation tab, where you can annotate all the files that you have in the project. You have the discussions, which is not like the GitHub discussions. You can compare between any files that you have in the project. So data files, code files, diff notebooks, comment on notebooks, etc. And you're going to have the pipeline here. So this is a version pipeline that shows you the flow of the project. And you can also easily reproduce the different steps of the project. And I think a best way to see like what DagsHub is all about is just click on the remote. And if you're going to click on the GitHub remote, you're going to see that you're getting the Git server for that project, right? So here on DagsHub, you're also getting the Git server that is connected to this project. But on top of that, you're getting the DagsHub storage here. That is a remote object storage that is configured with this repository and is managed by DVC. So DVC is an open source tool for managing large files, so versioning large files. And it's actually like an extension to Git. So DVC works with Git, and you can version your large files and simply push them to DagsHub storage. And you remember that I said that you can easily configure it with your local machine by us doing the DevOps heavy lifting for you. So in order to push your files to that storage, all you need to do is copy those 4 lines of commands to your terminal, and you're set to go. And by doing that and pushing your files to DagsHub, we'll be able to easily see them. So now I filter all the files that I have in this repo under DVC. And I can go to so those files are actually on our remote storage, okay? It can be an S3 bucket, it can be DagsHub storage, it can be Google Drive, like any S3 compatible storage. And I can easily view the files from here. So I'm gonna click on the examples and I'm gonna look for the predictions, and voila. I can easily see the images that I have in this project that are stored on my storage and view them, move between image to image. Not sure if you can really see it because they're kind of dark. And not just that, I can easily compare between images. So in this case, we had a bug when we developed the project where the model provided like the output of the model. This is the output of the model. So the model outputted an image that was fairly bright, and we couldn't figure out what happened. And then we saw that the hyperparameters were off, and we optimizing for the wrong metric, and then we reversed it, and we got those solutions. But we were able to easily diff between the different experiment and see the results. So I need to refresh. Internet connection is low. Awesome. So you can see that you can easily diff between image files. And this is, I would say, mind-blowing, because you're now treating your data as first-class citizen. It's no longer sits in like an S3 bucket in a different platform. You're using, I call it Stone Age versioning. So version 1 of the data, version 3 of the data, version that is ready for production, version that is really ready for production. So all of those name coding, I think it's bad because it doesn't allow you to reproduce your result at all. And you can also can't compare between them. So it doesn't really make sense to work like this. And this way you can diff between images, audio files. So for audio files, you can see the spectrograms, you can see the audio wave, and you can also listen to the audio file. You can diff CSV files, you can diff notebooks, you can diff all of those data types and formats easily from DagsHub. So now that we understand, yes.
Question: if you said we're diffing, for example, CSV and text files, in those contexts, it shows you, it highlights the differences or something? Because I don't know, it could be a lot.
Let's see. So here, this is like a small file that I can't really see the changes here. So maybe you'll see them here. Yeah, so basically, we simply mark with a yellow background the cells that were modified, and we show you the previous value with an arrow to the new value for all the different cells here. So this is a CSV file, and you see it as a table, right? Yes. Also a cool thing that you can easily filter. But if you're gonna have a diff, where can I find the diff? I'm gonna have to look for a CSV diff and send you later. But basically, you will be able to see all the different values that were modified. If you would have deleted a row, then it will show you that row with a red background. And if it wasn't modified, then it will have a white background.
Okay.
Can you visualize it mentally?
No, I think it's like like version control when you have.
Yeah, exactly. Like for code files, for text files.
Yeah,
any other questions?
Yeah, how much storage you can store, like images or big files or stuff like that?
So basically we provide 10 gigabyte of storage for community projects, but for this for the side quest, we're going to provide you with 100 gigabytes per project. And if you're going to need more, then just ping me and we'll figure it out. We're just going to probably need to make sure that you're not abusing the storage and like sending, like versioning Stone Age style and using DVC to version it. So like not version it properly and pushing it to DagsHub. But if we see that your workflow makes sense and you simply have like a large data set, we'll try our best to support you.
Especially if it's like a computer vision project. So
yeah.
Thanks.
Yeah. It's
Another question. You said before that you have your platform that you connect everything together. Maybe I missed it. So you're providing the storage by yourself, or you can link the outer storage service. Let's say I have AWS S3 buckets and everything. I can link them to you, and you will take care of the versioning and all what you said.
So I would say both, but then I'm not there are some caveats there. So you can either use DagsHub storage. Here, all the files that we have on here, like on DVC, the DVC version files are stored on DagsHub storage. That's like automatic, you get it out of the box. But you can also take your S3 bucket and connect it to DagsHub. And then you're going to have to version your files with DVC, push them to that bucket, and we'll be able to show it to you. So if you're just going to store your data there without versioning it with DVC, currently we don't support it. But if we're also paying a lot of attention to our community. So if it's going to come from the community, so we really we have a bottom-up approach. So if you're going to have like a use case where you have an S3 bucket and you're going to need to see the files from there, we might implement it. But basically also like the S3 bucket, like the S3 capabilities are more corporate issues and not community. Because if you're a community, you don't have issues to share your data.
Yeah, it's a question related just to my work now. So
you can connect your S3 bucket very easily to DagsHub and view the files from both, like from DagsHub, without the need to go to your S3 bucket.
Okay.
Any more questions? And okay, so another thing that is cool that I want to cover is the experiment tracking server. So as we said, we want to easily track our experiments. So with DagsHub, we integrated MLflow into the system, and you're getting a remote MLflow tracking server out of the box that is automatically configured with DagsHub. So in order to use that experiment tracking server, all you need to do is, once again, copy on the question mark, copy those 3 lines of commands that basically you're providing your username and password to have writing access to our server. Then you're running your Python script. In that Python script, obviously, you need to use MLflow to log your experiment. So like import MLflow and then MLflow.log metrics, and it will log the experiments to DagsHub tracking server, where you can visualize them under the experiment tab. And here you have all of your experiments. So you have the metadata about the experiment. You have the hyperparameters here with the bluish background. You have the metrics with the pink background. And not just that, you can, like, those are generated by Git. This is why you see the Git logo here. If it was generated by MLflow, you would see the MLflow logo here, okay? We're going to learn about both capabilities later on today. And you can easily compare between the different experiments. So just click on the experiment, click on the compare, and here you can see the experiment in a side-by-side view. So all the hyperparameters, all the metrics, etc. But if you don't have a golden metric, and if you're working in a production-oriented environment, you probably need to optimize based on a few metrics or hyperparameters, then you can easily choose them. So let's say the number of epochs, so how much time it takes you to train the model, and A1, A2, and A3 metrics. And here we can obviously see which experiment provided the best results. And also you have the side-by-side charts and graphs. And I think at that, we covered DagsHub at a very, very high level. As I mentioned, there's a ton of other capabilities like the annotation, that you can annotate and like label all the files that you have in your repo, the discussion that you can comment on all the files that you have in the repo, the data pipeline, the different capabilities, so a bunch of others. If you have any questions about that, I'd love to answer now. And if not, we're probably going to move to the more practical part of the workshop.
Can you repeat on the experiments? Is it like comparing models and metrics and all that? That's the meaning of experiment?
Yeah, please. Also, like, how did you get those things? Like, for example, you set the your metrics and results and the hyperparameters there in the Git, so it will read from the Git, or how it will take it?
Once again, excellent question, because because I have a slide about it.
Yeah,
So
in
we're
like
gonna cover.
okay.
So we're gonna cover it in 5 minutes actually. How you can create experiments using Git. So for that question, we're gonna cover it in a sec. But basically, experiments here. If you're logging them with MLflow, you're simply dumping all the information to that server, and we're gonna visualize it here. And with Git, you're gonna do it in a different way. I don't want to cover it now because we're gonna cover it in a second. But basically, an experiment is a set of hyperparameters and metrics, right? So you change the hyperparameters. It can be like a different model. So maybe ResNet and not VGG19 architecture, whatever. You can also generate your own hyperparameters, and you have the metrics that you want to follow because you want to optimize based on something. So you want to log all of this information, and we simply provide a place to visualize it. With Git, we also provide you the ability to reproduce the experiment, and we're going to see it in just a bit how we can do it.
But the experiment itself is the models, right? The models and the parameters and the metrics that change.
So not the model, just an experiment is a set of hyperparameters and the output, the metrics. Then you can see which provided better results. If you want to reproduce it, if you want to get the artifacts, I think it will be much more clear in just a few minutes. And if not, stop me after we're going to finish talking about the experiment tracking. Okay, so with respect to time, I think it's a good time to move to the second part.
Excuse me, are you planning to have some breaks in this session?
Yes, so we're gonna have the experiment tracking session now. It's gonna take roughly 10 minutes. Cool, so before the break, we discussed about what are the challenges when working as a team on a data science project, and what are the elements of a desirable solution to overcome those problems. And we're gonna, in this section, we're gonna explore two core elements, which one is the experiment tracking, and the other is the data version control, or basically version everything. And we're gonna start with experiment tracking, as you can see. And for when we talk about experiment tracking, there are two main approaches. So the first one is, can you see my screen, by the way?
Yeah.
Yeah, you probably would have stopped me. So we have the external tracking, which is basically means executing an experiment, and during running our code, we're gonna make calls to an API to log the information of the experiment to a database, which can later on show it. Or we're gonna use the GitOps approach, which we can define each experiment under as a Git commit. So every Git commit or an experiment can be a Git commit and not vice versa. And let's dive into those options. So we're going to start with the external experiment tracking. And external experiment tracking has two main advantages. First and foremost, there are very good existing tools out there, like TensorBoard, MLflow, ClearML, weights and biases, and more that are simply taking all the information and of the run and dumping them into a directory or a file and making and showing them under a table. And this is also probably the most intuitive way to log things. So we have a new experiment, we run it, we log it to some database, and then we see it in a table as a new row. However, using external those tools to track and version or to track our experiments can easily get us spaghetti. And what do I mean by that? When we run multiple experiments, we're going to end up with a huge table of experiments where we have no idea which experiment is connected to which code or data file. And it's going to be very unclear to connect the run to the relevant code. And this is especially hurts when we try to understand and review the work process or the research process our team member did. And it can also be the future you in 2 weeks. And last, it makes it unclear on how we can reproduce the different runs. And taking those considerations under account, let's talk about the Git tracking approach. So when we track our experiments with Git, we have a single source of truth. We can easily know what code, data, and model produce that results. And not just that, we can easily reproduce the result by simply using the git checkout command. And that provides us the experiments with their context. And also, Git was designed to model parallel work. And it will enable us to work simultaneously on different project components without stepping on each other's toes. Unless it will unlock GitOps for us using CI/CD tools and automations to easily integrate, migrate, merge, and deploy the different code components or experiments once we're done. However, it can get complicated really fast when we're going to grow in the number of experiments, because we're going to have a lot of Git commits, and it's probably going to be a big pain when we also want to go back for previous versions of our code or data or models. And also, it's less intuitive because we need to do something active in order to log it, and we need to use Git, which wasn't designed for it. So my recommendation in this case is not to choose between those two approaches, but simply mix and match. So let's say we're testing now a new hypothesis and we're starting to play with our code. So there is no real meaning in encapsulating this experiment with a Git commit, right? Because we wouldn't want to reproduce it. So let's just automatically log it with this logging tool, let's say MLflow or weights and biases, if you're familiar with them. And once we're going to reach a desirable state, so let's say we reached a very good results in our model, we're going to simply encapsulate all the relevant components with the information of the experiment under a Git commit in a way that will enable us to reproduce a result easily later on. So we're going to use both approaches in our workflow. And let's now talk about the how. So the what is clear for everyone. Any questions about the how or about the what? Okay. So moving on to the how we can do it, I'm going to start with the external tracking tool. And today we're going to talk about MLflow, which is the most common experiment tracking open source tool out there today, maintained by Databricks, and it provides support to the entire lifecycle of a machine learning project. And we're gonna focus on MLflow tracking, which is an API for live logging of parameters, metrics, metadata, and artifacts from a machine learning code. And how can we really use it? So let's say we have our code base, and now we want to log the relevant information from our experiment with MLflow. So what we need to do is simply install MLflow in our project, then import MLflow to our code, and start logging the relevant information. So how can we really do it? As you can see, we can use the MLflow log params and MLflow log metrics to log the relevant information. And MLflow will log them differently because one is a parameter and the other one is a metric, right? We can also, MLflow has more capabilities, like let's say the auto logging. So if you're using one of the commonly used frameworks like TensorFlow, Keras, PyTorch, sklearn, FastAI, etc., you can simply import MLflow, then add one line of code, which is MLflow dot the name of the framework, let's say Keras dot autolog, and it will automatically log the information of the experiment to your database. How powerful is that? You don't need to do anything, and you have everything saved in some magical database. And now you can see the information of the experiment either in your local database on your machine, or to log it to a remote tracking server and have it accessible to all of your team members. However, if you are working in a team and you want to run your experiment on different machines, or you're working with a remote machine or whatever, you do want to use an external remote tracking server, right? And this is where MLflow is a bit tricky, because setting that remote tracking server can be a bit of a hassle. And we're not DevOps people, and we don't want to deal with those types of issues. And also we have problem with team-based access. So maybe we don't want all the team members to access our experiment tracking server. We want to provide it to a specific group in our specific team in our group to have access to it. So this is where DagsHub comes to the rescue. And as we saw, we provide an MLflow tracking server that is automatically configured with your repository. And you can start logging your experiments by simply copying those 3 commands that we just saw to your terminal, and then run your Python script. Obviously, you're going to have those lines of code there. So the MLflow.log params or metrics or autolog. And by running it, you'll be able to see the experiment under the experiment tab while the experiment is still running. So let's say we talked about computer vision projects, right? You might run an experiment or train your model for a week. You don't want to just like run it for a week and then get the bill for Amazon and also understand that you didn't provide any good result, that the model didn't converge, right? So you're only gonna eventually pay the bill without getting anything out of it. You want to see the results of the model while it's still training. So with MLflow, you can log the information while you're still running the experiment, and it's gonna show it here as a graph under the experiment tab in DagsHub, okay?
This is the log you get from MLflow API, right?
Yeah. So you use the MLflow package or tool to log the experiments. You log them to DagsHub servers, and you can see it under the experiment tab on DagsHub. Okay. Make sense?
Yeah. This is the log. What you're saying right now, it's the log of the MLflow.
Exactly. So this is the table. This is the table, and let's say I clicked on the first row. This is what I'm going to see there under the, like inside the experiment itself. So moving on to the Git tracking. So we know that many data scientist teams or many teams are adopting Git as their tool to manage their project, which is really great. So this is why we decided to support it also as the experiment tracking tool. And how does it really work? I missed a bullet. So Git tracking for data scientists. So how does it really work? So basically what you need to do is log the information of the experiment to open format files that ends with params.yaml for parameters and metrics.csv for metrics. You can have a prefix for them. So the best, like ResNet model parameters, params.yaml, and it will, you have the prefix, but it needs to end with those specific names. And once you're gonna commit those files to Git and push them to DagsHub, we're gonna parse the commit behind the scenes. We're gonna look for those special files in the commit. And if you're gonna find a new one or an updated one, we're gonna simply generate a new experiment in your experiment table. And why is it so powerful? Because now you can encapsulate all the information of the experiment, including the metrics and the parameters, under one Git commit, which will enable you to reproduce those results easily. And not just that, you can use DagsHub UI to compare between different experiments and see which one produced the best results. And to make your life much more easier, we created the DagsHub logger, which is a basic Python logger that you can install by running pip install DagsHub. And the way that you can use it is either as a context manager or a normal Python logger. But basically, as we saw for MLflow before, all you need to do is log your metrics and hyperparameters. And when you're going to finish running the code, it's going to output this information to the files that we just talked about in the needed format. And all you need to do is version them with Git, push them to DagsHub, and it's going to create a new experiment under the experiment tab. So as I said, you can also use it as a normal Python logger. And that's pretty much it, as simple as that. So any questions about it, about GitOps or Git for experiment tracking? All clear? Wow, this is amazing. So you're very, either you're very, it was very easy to get to the aha moment, or you're very tired.
No, I am thinking.
No, it's cool.
Can you show us an example? Like, do you have a one that you are going to run on live?
So what next we're going to cover, because I want to do it all at once. So we're going to cover how you can version your data with DVC, which is like a different topic, the last topic for this session. And then we're going to see how we can use those tools to implement those capabilities. Awesome. So
MLflow, but DagsHub, like API.
No, so we don't provide live logging or the ability to log your experiments to a database. We simply output the information to those files, so open files, a YAML file and CSV files. And because it's going to be with a specific naming convention that we use, and in the format inside, it's going to have like the relevant format, then we're going to be able to see it to parse it and show it in the experiment tab. We're going to see it in just a bit, like right after the data version control, how it's done.
Okay.
But we does it all make sense with respect to like how to track, why we need experiment tracking, how we're tracking our experiments?
Yeah.
Awesome. So moving to the final part of the session, which is the data version control. So when we talk about versioning our data or our files, you might be asking yourself, okay, so why not simply use Git to version it? So Git was originally designed for managing software development projects and for versioning text or code files. Therefore, Git doesn't handle large files very gracefully. And now you're going to probably ask me, okay, so why not simply use Git LFS for this task? So Git LFS is better than Git for managing large files, but when scaling or having multiple images, it fails. And this is based on user interviews that we're doing with a lot of companies and ML engineers and data science practitioners. So in addition, both Git and Git LFS are missing a lot of core capabilities that we need as data scientists, such as providing a pipeline and reproducing a pipeline, importing files from different projects or data sets from different projects, etc. And to overcome this problem, a lot of powerful tools and platforms emerged in recent years, such as MLflow that also supports versioning of large files, Pachyderm, LakeFS, Delta Lake, you name it, they provide it. And the most commonly adopted tool in the industry today would be DVC as an open source tool. And DVC stands for Data Version Control. And it's basically a CLI tool for data scientists to manage their project and version their work and easily reproduce it. And DVC actually was, if you want to think about it, it was designed based on Git, and it works as an extension to it. So it means that DVC doesn't replace Git when we try to manage our projects, but it works as an extension to it to version and manage our large files. Also, it enables us to version all of the project components and save them either locally or in our remote storage. It provides us the ability to easily reproduce our results And it also supports pretty much all the cloud providers. I don't like to say all, but most of the major cloud providers like AWS, Google, Azure, Linode, etc. It handles large files very well, better than Git and GitLFS, according to people that we know that uses both. And last but not least, DVC is open source, which I'm very excited about. And I think it's great because you don't have a vendor lock here. And it supports all different platforms like Linux, Windows, Mac, etc. So before we're going to dive into DVC usage, I'd like to better understand what is the workflow of using Git and DVC at a very high level, okay? And I feel like this is something that our users said, like a lot of our users are saying, that it helps them to better understand how to use DVC in their workflow. So let's say that we have our data directory, we have our Git tracked files, and we have our DVC tracked files. They can be, let's say that they're on our remote, okay? And we're gonna start by adding this huge file to our project, which is the universe.txt. And this file holds all the information that we gathered along the years about the universe. And obviously, it's not going to be a good idea to version it with Git, right? So what we're going to do, we're going to version it with DVC. So now we have version A of our file versioned with DVC. And by performing this action, it's going to generate, or it's going to create two actions. The first one is going to tell Git to ignore this data file. So it's simply going to add the universe.txt to a git ignore file, okay? And also, it's going to generate a pointer file that is named the universe.txt.dvc, okay? This is a pointer file that points to the specific version of our data file. So this pointer file is going to point to version A of our data file. So those two files are going to be versioned by Git. And as a rule of thumb, every file that ends with .dvc, we're going to version it with Git, because those are small files. So now that we have it on Git, let's see what we can do next. So let's say that we Ari is working on pre-processing the data, and he generated a new version of our data files, okay? Let's call it version B. So as we can see, we have in our file system a new version of our file, version B, but the pointer file is still pointing on version A. What we want to do next, we want to version the new data file with DVC. So we're going to run here the DVC add command for the universe.txt once again. And this is going to version the data file with DVC. And as we can see, it's going to generate a new pointer file that points to version B. Okay, so far so good?
Yeah.
So we version it once again with DVC. DVC, what it did, he created a new pointer file. Next, what we need to do, we need to version the new pointer file with Git. So we're simply going to run git add the universe.txt.dvc. Okay? And let's say we're going to do this process again. So try to think what will be the workflow. So let's say that I process the data again and generated a new version of our data. Try to think what will be the workflow now. Don't answer. Let's take like 10 seconds just to think about it. I'm gonna zip some water.
Sorry, what was the question again?
What will be if I'm gonna, now I created a new version of my data file. What will gonna be the workflow to version it with DVC and Git? So just take a few seconds and try to think it through. Anyone from the crowd that has the answer?
First is going to be to DVC. I see.
Okay, we version it with DVC.
At the end in Git, add the C.
Get a pointer.
The pointer,
Yeah.
yeah.
Awesome, exactly that. So we are versioning the data file with DVC. DVC generates a new pointer file that points to version C of my data file. And then I'm gonna version the pointer file with Git. Okay, as simple as that. And now let's see why we're actually versioning why we have this pointer file and why are we versioning it with Git, okay? So let's say that at this point where I have version C in my file directory, I want to go back to version A of my data file. How can I actually do it? So what is the workflow here? We're gonna start by going back to the relevant version of the pointer file. So we're gonna use Git to find the pointer file that points to version A. And we can either use the git checkout command or the git reset command. Depends if we only want to go back with the data file or want to take the entire state of the project back. Then we're gonna revert back the pointer file. So now we can see that in our file, in our local directory, we have version C of the data file, but version A of the pointer file. And next, we're gonna use the DVC checkout command or the DVC pull command that are basically, either if you're using it locally, so let's say if I version the files locally, I can use the DVC checkout command. But if version A of the file is on a remote storage, I'm gonna have to pull it to my local machine, right? So I'm gonna use the DVC pull command. And now once I'm gonna run those commands, DVC is gonna parse in the storage or in our cache directory for the relevant data files that matches to the pointer file that we have locally. And it's gonna simply push the data file to our local directory. And by that, we managed to go back in time with our data files or large files.
All the data files are stored on the DVC?
Yeah, so the DVC, this cloud that we see here can either be a remote storage or the DVC cache directory that we have locally. So basically, if you run everything, if you're versioning everything locally, DVC, or not everything, DVC uses a cache directory where he stores all the versions of the data files. So locally, you're gonna have this cloud with all the different versions. But let's say that Philip wants to have access to version A, and you have it locally and you pushed it to the cloud. So Philip is gonna have to pull it from the cloud, right? So Philip is gonna have to run the DVC pull command.
But it can be very large to store all the different data files.
So this is a good point. So DVC uses hashing to hash all the files. So let's say you have 1,000 images in a file and you version it with DVC, and now you only change one image in that directory, okay? DVC won't create a replica for all the 1,000 images in the directory. It's gonna create a replica for only the specific file that was modified. So this way it's not like Git where it creates replicas of all the different versions. It knows which file you modified, and it only creates a replica for that specific file. And this is the optimized way to do it. And also, if you think about storage nowadays, they're fairly cheap. And currently people are doing like Stone Age versioning. So they're not really using like an external tool to version their data. They're just like dumping everything in different versions. So this is probably going to be optimized comparing to any other workflow that is currently implemented in the industry, and much more easier to reproduce because you're basing it on Git commits, which is very intuitive for us as developers. Awesome. So because of time, I'm not going to cover the dark side. We all know that DagsHub provides you a remote storage out of the box. So this is the caveat here. And I'm going to dive right into the DVC 101. And in the DVC 101, we're going to cover the basic commands that DVC has that will enable you to get started fast with it. And we're going to see how we can set up DVC and connect remote storage to our local machine, how we can version files using DVC, how we can push files to a remote, update different versions, and go back in time. Okay? So I'm going to start by initializing DVC. So I'm going to go from my command line, from my terminal, to the relevant directory. Please make sure that you're in a Git directory, otherwise it's not going to work. And I'm going to run pip install DVC. So the pip install will work, but the second command won't. So I'm going to start by installing DVC. And then I'm going to run the DVC init command that is basically going to initialize DVC in that directory. And what will it output? It's going to create a .dvc directory. And this directory holds all the relevant information about DVC, the logs, the cache directory that holds all the replicas, etc., and a .dvc ignore. And this file acts like the git ignore, but for DVC. I'm not sure if which one here is using Mac, but every time that you create a new directory on Mac, it creates the studio file, so like this random file, and you don't want to version and push it to the remote. So you can add the name of the file to the DVC ignore, and it won't version it. So we want to version the .dvc file as we said with Git, because our rule of thumb here is if it ends with the .dvc, Git is going to handle it and commit the changes. And now we're going to want to set a remote DVC storage, the DagsHub storage, with our local machine. How can we do it? We're going to go to our DagsHub repo, and we're going to click on the remote. Then we're going to click on the question mark next to the DVC remote, and we're going to copy those 4 lines of commands. And we're going to paste them to our terminal. And what those commands hold. So the first one is the DVC remote add, and we're basically adding a new remote, the same as we would like run git remote add. Next, we're giving the remote a new name, which is going to be origin. And we're going to use the local flag to use it as a local, to store it in our local configuration. So a side note, if you're going to use the local flag, it's going to save those configurations in the .dvc local config file. And this file is not tracked by Git. So it's in the git ignore file. And this way, you're not going to push it to your DagsHub remote, or you're not going to push it to the remote. Why is it important? Because you don't want to set your credentials to DVC, accidentally version them with Git, and push it to the remote to have it accessible to your collaborators. And the last thing here is going to specify the URL for our remote, for our DVC storage. And as you can see, it's basically the URL for our remote repository with the .dvc ending. So the same with Git. The last 3 lines is basically providing the credentials to DVC to have write access to the remote storage. And let's see what we actually did here. So as we can see, if I'm gonna see the local configuration, I'll be able to see the URL of the remote, the username, the authentication, and basically I'm gonna see the password here. And now what we're gonna do, we're gonna use Git to version it. So simply git add and git commit. So we're gonna version the configurations that we just added. And now we reach to the point where we're ready to create this mega file. And this mega file is gonna be the universe.txt. And we're simply gonna dump the entire universe to that file. And because this is a very large file, what we're gonna do, we're gonna version it with DVC. And how can we do it? We're gonna use the DVC add command to add the universe.txt to DVC tracking. And next, we're gonna specify the path to the file that you want to version with DVC. And the coolest part with DVC is that it's kind enough to specify what modification or changes he did to the project that we need to version with Git. So as we can see, it specified that he created the .dvc pointer file and a git ignore. But let's not trust DVC and see it with our own eyes. If I'm going to run the git status, I can see that DVC modified the git ignore and generated a new file named universe.txt.dvc. Okay, so now what I want to do, I want to use Git to version both of those files. But before I do it, let's see what those files holds. So I'm going to start by seeing what the .gitignore file holds. So as we can see, it simply added the universe.txt to our gitignore file. But more interesting is what the universe.txt.dvc holds. So this is a pointer file that, as we said, points to the relevant version of our data file, right? And how does it really point to it? So DVC uses the MD5 hash to hash the version of the data file and simply connect between that pointer file to the relevant version of our data file. It also stores the size in byte of the original data file and the path to it. Someone open the mic, so any questions? Okay, so this is the pointer file.
It's the same as Git, more or less.
The same as what?
As Git, like if I want
as Git pointer file. Yeah, so this is what Git does behind the scenes pretty much. So it like has the relevant commit that is connected to the relevant hash. But with DVC, you're doing part of the work in front of the scenes, so it won't automatically version all the different changes. So now what we're gonna do, we're gonna simply add those files to Git tracking. So run the git add command, and we're gonna specify those two files, and we're gonna commit the changes. Next, what we want to do, we want to push those files to the remote to have them visible and accessible to all the team members, right? So we're gonna use the DVC push command, and then we're gonna specify the name of the remote that we want to push it to. DVC would either ask us to provide with our username and credentials, but if you're using the current version of the command that we're providing, then it won't, and it's gonna simply push it to DagsHub. However, if you're gonna go at this point to DagsHub, you will not see that data file. Why is that? Anyone can think why you won't be able to see that data file on DagsHub currently?
You need to do commit, no?
So no, I pushed it. It's on the file is stored on the remote storage.
You're only looking at the pointer now?
Okay, you're in the direction. What is this pointer file? How do we maybe use it?
Yeah. Afterwards, you said it's doing hashing and stuff. Maybe you need to do some sort of compiling behind the scenes to see the file itself.
To the point-ish. So basically, behind the scenes, what we're doing what DVC does when we talked about reproducing previous results or previous versions. What DVC takes the pointer file and looks for the relevant file that it points to, right? So the same with DagsHub. What we're doing, we're looking for the pointer file in the current commit that you're looking at. We're parsing the storage and we're showing the relevant files in the UI. So now, because we only pushed the DVC tracked files to our remote, we won't be able to see them in DagsHub UI because we didn't push also the relevant pointer files, right? So now if I'm gonna use Git to push the pointer files to DagsHub, and I'm gonna go to DagsHub, I'll be able to see the universe.txt file in DagsHub. Okay? Make sense? Want me to repeat it?
You can also upload it manually, no? Upload file.
No, so upload files, you're gonna upload it to Git and you're gonna have to commit it. With DVC, you currently need to use the CLI command, the CLI, to version things and push them to DagsHub. And we can also see here that we have that pointer file that points to the universe.txt. So this is important. If we wouldn't push it, we won't be able to see all those, like the relevant data file. And at this point, let's say that we decided that Bitcoin is gonna replace the way that we're gonna trade. And we want to add Bitcoin to the universe, right? Genius idea. So we're simply gonna add Bitcoin to our universe.txt file. And we can see that we added another line to our DVC tracked file. And I would ask you, what will happen now if I'm gonna run the git status command now that I edited the universe.txt? What git status will...
you also updated DVC first?
So you're saying that Git will show that this file was updated?
No. Like
Okay.
you said
What?
before that first we need to update DVC and then Git. Okay, because Git right now is going to a pointer. So
right.
First,
so
we need to update the pointer that is updated by DVC.
Exactly. So if I'm going to run git status, I'm not going to see any changes to my file, right? We're going to be up to date because we basically didn't modify any file that is tracked by Git. We only changed the file that are versioned by DVC. So if I'm going to run the DVC status, which is another command that we just learned about, we're going to see that we do have a file that was modified. The universe.txt was modified. So in order to version this new file or the new version of the data file, we're going to once again run the DVC add command. And once again, DVC is going to let us know that he updated the pointer file. And if we're going to see what the pointer file holds, we're going to see that we're going to have a new hash, MD5 hash. Trust me, it's new. It's not as the previous one. We're going to see that the size of the file moved from 13 bytes to 21 bytes, but the path didn't change. And now what we want to do, we want to simply version the pointer file with Git and commit the changes. Awesome. Let's say that we also push the files to DagsHub remote. And at this point, I talked with Asi, and we decided that Bitcoin is horrible. It's very, very bad, and we want it out of our universe. We don't want to use Bitcoin anymore. It's crashing our economy. So how can we really revert back, right? It's going to be very hard. It's DVC, and it's a large data file, etc., etc. So what we need to do next, we're going to need to simply revert back the pointer file that points to the version without Bitcoin. So what I'm going to do, I'm going to run the git ref command, and I'm going to look for the relevant commit that points to the version A of my universe.txt file. So we can see that this is the relevant commit. And what I want to do next is simply run the git checkout command, add the 7 digits or characters of the commit, of the relevant commit. And I like this, like in this use case, I only want to revert back the data file. But if you want to revert back the entire state of the project, then just don't add the name of the file that you want to revert. And now, if I'm going to look what I have in my pointer file, I can see that it went back to pointing at a file that holds only 13 bytes. So it doesn't have the Bitcoin line, right? It points to a file that has only the universe. But if I'm going to see what the universe.txt holds, what I'm going to see there. So if I'm going to run the cat universe.txt.
You changed the pointer. Let's see. You're changing the pointer, so it should be pointing to the one that doesn't have Bitcoin.
The file itself wasn't changed yet, no? So it still have the data.
So the pointer file was modified. So the pointer file currently points at the version A of our data without the Bitcoin.
It should show the one without the Bitcoin, because now you're changing the pointer now.
Okay, so this is important. Without running any DVC command, we won't change any of those files. So even if we're going to modify the pointer files, if we're not going to run the DVC checkout or DVC pull command, the data files are going to stay the same. So it's not really like using DagsHub, where you have your storage and your pointer files and we parse them. You need to use, you need to actively use DVC to revert back to the relevant changes. So now, as you can see, I still have the Bitcoin line in the universe.txt. What I want to actually do now is run the DVC pull command. Also, running the DVC checkout command would have worked now because I version it locally and I have it in my cache directory. But if I'm going to run the DVC pull command, and I'm going to specify the name of the origin or the name of the remote, I'm going to see that it modified the universe.txt. And now if I'm going to run the cat universe.txt, I will see that it only holds the universe line.
This is the original, like
yeah,
file.
Version A of my data file. Any questions so far? Or that's like, this is the DVC 101 crash course.
Maybe I will be skipping a few things asking this, but so DAGs will simplify this, and we choose one command will cover the at least two commands we need to make the changes if we use DVC and Git on our own. So
we have a wrapper tool, so that wraps both DVC and Git. This is not something that we currently cover. You can look it up. It calls Fast Data Science. And this tool is like a wrapper for Git and DVC, and you can easily use it. So basically using only one tool to version both your code files and data. But in this case, no, DagsHub doesn't do anything that relates to versioning the data and code files. You're doing it with those two tools. The thing is that you can push it to DagsHub storage easily without configuring anything. So let's say if you would want to use an S3 bucket, you're going to have to open an S3 bucket, define a user, a role, have access to that bucket. A big ass hassle that is going to be how to push your data, the version data, to a remote and have it accessible to the teammates. So this is where DagsHub really helps. It lowers the barrier with respect to the remote storage. Make sense?
Yeah. So the hassle of the box is outside.
Yes. Or you can check. You can look up for Fast Data Science. I will be happy to share links. I think I'm gonna probably send Mo some links so we can send it to you on Slack. I'm not sure which platform you use, and you can so for reference and stuff like that. Okay, so. Any questions so far? Speak now or forever hold your peace before moving to the showcase.
How do we use the count for our projects?
So this is what we're going to cover next. I'm going to show you how you can use your GitHub repo. Sorry, it bothers me, so I'm going to end sharing. It probably drives you crazy. So basically, I'm going to show you next how you can connect your GitHub repo to DagsHub, and without the need to really using both platforms. So you can manage the entire project from DagsHub. So managing pull requests, issues, etc. So all the Git features, and using the rich data catalog, the notebook diffing, etc. from DagsHub. So I'm going to do it right now. But any questions about the data versioning or the experiment tracking?
Pretty clear.
Awesome. So we're a bit tight on schedule, so I'm gonna run it through. So let's start by showing how we can connect a GitHub repo to DagsHub and what we can benefit out of it. So what I'm going to do next, I'm going to simply open a new repo on GitHub. Let's call it ITC test. And I'm going to make it public. I'm going to get the README file, a git ignore for Python. And I'm going to create a repo.
You can't make it private?
Yeah, you can. Just
Okay.
made it public randomly. Next, I'm going to go to DagsHub. I'm going to click, wait, let me see the regular UI. I'm going to click on the create button. I'm going to click on the connect a repo button. I'm going to choose the GitHub Connect option. And next, because I also already provided access to DagsHub from my repo to my GitHub account, you're going to probably need to provide us access to your GitHub account. Next, I'm going to look for the ITC test. I'm going to choose it, and I'm going to connect the repo to DagsHub. And as simple as that, I have the GitHub repo connected to DagsHub. We're going to sign that repo to an API agent that every time that you're going to push the code to GitHub, it's going to also be updated on DagsHub. The same for pull requests and issues. So if you're going to open a pull request on GitHub, you're going to immediately see it on DagsHub, and the same for issues. And if you're going to close a pull request or an issue from DagsHub, you'll be able to see it also on GitHub. So this is like, you don't need to move around between the two platforms. You can simply use DagsHub to manage everything. And as I mentioned, you're going to keep the Git server on GitHub. So you see, you don't have a DagsHub Git server. We're using the GitHub server, and everything stays there. So it's still here, right? I'm going to refresh it. Nothing changed. And what we're going to benefit out of it. So if I'm going to go to this project, let's say this is a research group from Germany who is trying to use satellite images to see the effect of crops, etc. Never mind. So if I'm going to go to a notebook and I'm going to check the history of the notebook, let's say, I'm going to choose this history. Oh, wait, I want to copy the commit. I'm going to copy the commit. I'm going to choose this notebook. Look carefully, because this is very interesting. GitHub won't be able to load the diffs of the relevant notebooks, because those notebooks has outputs, which are images, and GitHub can't parse them, okay? And if I'm going to go to the GitHub connected repo, so this is the same repository that is simply connected to DagsHub, and I'm going to compare between the relevant commit to master, and I'm going to go to the same notebooks, I'll be able to see the diff in the notebooks, between the different notebooks. So what cells I edited, what cells I modified, and also see the outputs of the training. Oh, they don't have images here. So some notebooks have images. So we're also going to diff the output of the model. So the relevant images. Same for this project. So this is a different project. And if I'm going to go to the data directory here, I won't see anything. I will only see the the pointer file, the DVC pointer file. But if I'm going to go to the DagsHub repo, and I'm going to go to the data file, the data directory, I can magically see those data files, the process and raw that are hosted on my DagsHub storage. So I'm going to enjoy the best of both worlds. And not just that, if I'm going to go back to this project, here Kuyen, what she's doing, she's using GitHub Actions to automate the deployment and test processes. So every time, so if I'm going to go to the GitHub Actions, so every time you open a new pull request, it's going to go through a series of tests that is going to test your code. And if a pull request is merged to master, you're going to go through a CI/CD process to automatically deploy the new model to Heroku servers. So let's say I'm reviewing my project on DagsHub, where I can see the data, the code, the model, everything. I can diff everything from DagsHub, and I see that it works perfectly. And now I want to merge it and automatically ship it to production. So I can use GitHub Actions to do it. So this is a really good use case where you can see that you can enjoy the best of both worlds. So use the rich data catalog on DagsHub and the diffing capabilities, but on the other hand, use GitHub Actions to automate your workflows. Make sense? questions about connecting repos?
So you link to Rocco for deployment, and every step you take in DagsHub, it's automatically update?
No, so she created specific GitHub actions for the specific use cases. So if I'm gonna go to the YAML file to deploy the model, so you see that it's deployed the app on push to master branch. So this is like the YAML file for GitHub actions. So she did it by herself. She obviously used like predefined YAML files to automate the process. But basically what it does, every time that she merges a new commit to master, it goes through this pipeline and eventually deploys the model to production. In this case, she used Heroku. You can use AWS services, you can use Google, you can use whatever. And you can have like different use cases or whatever to specify
conditions.
When you want to different conditions that you want to deploy the model based on or to use the test on. So merge to master, open a pull request, push any commit, so anything that is relevant for you. And she also like specify if there is a push to master and files that were changed in those specific paths. So if you change the data files, you don't need to, and you merge them to master, there is no need to deploy a new model to production because the latest version is there. So this is just like examples of how you can benefit from both GitHub and DagsHub, and why I highly recommend using both platforms. So first, don't open the project solely on DagsHub because obviously you want to also like use it to share it with your your friends, or use it as part of your portfolio, which is also it's acceptable because a lot of people currently uses GitHub, but you'll also be able to use DagsHub for it and view all the different components. And just a note, we currently see some users that uses DagsHub as the place for their portfolio. So they're hosting all of their projects on DagsHub, showing the models, the experiment, all the research phase. And this way, for me as employer, I'm able to review all the research process that you did and not just the code files that I can do on GitHub.